Alrighty.
All right.
Should I share my screen now, or you want to do an intro? What do you want to do?
Well, I'm gonna introduce you.
Okay.
I'm Glenn Reed. I'm K5FX, and I'm the host for this webinar session. Our presenter is Alan, W2AEW. If you don't know, Alan has an extensive QRZ and YouTube page, and I can say he shares the same admiration I have for D104 microphones. So, with that, Alan, please, please proceed.
Okay. Let me do a quick share here. Make sure
Uh,
everybody can see the presentation. Go into
you're
full
good.
screen mode here. Let's see. Everybody got it in full screen now?
You're good.
All right. Let me go in. I want to bring a laser pointer up to make it easier for people to see things here. Alrighty. Um, yeah. So today, well, thanks again for being the tail gunner here on the G-QRP convention. I got up real early for the opening session at 5 a.m. Here in New Jersey yesterday. It's a couple of really great talks, and probably one of the things that I heard in most of the talks that I listened to was a NanoVNA. So Heather gave some great information on it. Pete talked about it. Hans talked about it. So let's see what we can learn about it. Maybe fill in some of the blanks and any that anybody may have in their understanding of it. And then, of course, we'll take some questions here later. All right, so here's our agenda. Why do we want to talk about this nano VNA? And the reason is that these ridiculously inexpensive nano VNAs now make VNAs accessible to hobbyists, ham radio operators. U.S. price is $50 to $60. You have to do your own conversion to wherever you are. So now we've got access to this tool. But a VNA is something that was traditionally only available to kind of professionals. So, and a lot of people aren't familiar with what a VNA is. So we're going to talk about that first. Then we'll talk about what a VNA is good for, and then we'll take a look at the nano VNA and talk about things like calibration and different types of measurements you can make, and the good, the bad, and the ugly. So first, what is a VNA? Well, VNA stands for Vector Network Analyzer. And if you do a quick Google search on VNA or Vector Network Analyzer, you'll probably come up with a definition like this, something like an instrument that measures the magnitude and phase of the reflection and transition properties of the ports of a device versus frequency. You might say, what the heck are we talking about here? So let's break this down and try to clear this up for everybody. So a VNA, it's an instrument that's used to characterize RF devices, and it could be anything from components to filters to antennas to any number of devices. And as I mentioned, it used to only be used by professional RF engineers due to cost. The instruments that I've got shown here on the top and the middle one here are relatively inexpensive VNAs, and they're in the range of $5,000 to $10,000. I don't know if anybody wants to venture a guess to this kind of top of the line 4-port PNAX from Keysight, but that is about $240,000. So pretty amazing. These things typically are not in the hands of any hams, right? But now they can be. Now, of course, when we talk about VNAs, and if you pick one up and you start doing some research on how to use it, you're going to run across a ton of acronyms and different terminology than you might be used to in the amateur radio world. So we're going to touch a little bit on that too, so that at least it'll help you to speak the same language as folks that are professionally using VNAs. So the first is a DUT. What is a DUT? A DUT is a device under test. And it could be your antenna. It could be your antenna system, including the coax, the feed line leading to it. It could be a filter. It could be a duplexer. It could be a diplexer. It could be something like that. It could be just a component. Anything that's you're testing, we'll call it a DUT. And in the literature, you see DUT, that's what we're talking about. Any DUT is going to affect the signal that's applied to it and going through it in one way or another. And that's the whole reason you're using a device. You want it to do something. The input impedance of that DUT is going to affect the signal that's being applied to it. And as everybody is kind of aware, in order to get maximum power transfer from any kind of a source, whether it's an RF source or anything else, you want the source and load resistances to match. In a more general sense, you want the impedances to match. And really, in the more general sense, if you've got a complex source impedance, you want the load to look like the complex conjugate. We're not going to talk too much about that, but it just kind of illustrates the point that you need to know really the complex impedance characteristics of a device in order to make the most use of it and get the best impedance or power transfer into a device. But this is why we talk about this. Now, when we talk about RF signals, we like to think of signals as waves. Okay, and rather than talking about just voltage and current, like we do with DC circuits, we want to talk about magnitude and phase. And just like we're just showing two sine waves here that are varying in magnitude, and they vary in phase, or delay is another way to think of phase. And this little moving diagram here is just intended to illustrate if I had some kind of a magical sliding transmission line that was getting longer and longer between a source and a load, the reflection coming off of that load will move with respect to the source going in. And this is what gives rise to standing waves on transmission lines. But we'll talk a little bit more about that later. So we want to be able to characterize the magnitude and phase. So if we got a source applying a signal to a DUT, okay, that's kind of shown in the green arrow there. Two things are going to happen at least. One is the signal is going to go through that device. So we want to understand what the DUT does to that signal. Does it attenuate it? Does it amplify it? Does it filter it? Does it change the phase, etc.? Does it change, how much of a delay is there? All of those are transmission properties. But also, if we don't have a proper complex conjugate impedance match between our source and our DUT, we're going to get some reflection. And we characterize that reflection in a number of different ways: SWR, return loss, reflection coefficient, etc. All right. So the DUT reflection and transmission will again alter the magnitude and phase of the source signal. And this is what a VNA characterizes. So this is what a basic VNA looks like. We've got a source right here that's providing an RF stimulus that is ultimately being applied through port 1, that's a traditional name for it on a VNA, to the DUT. And the DUT then, if it has an output, not all DUTs have outputs, if it has an output, that is measured essentially on port 2. Now, in order for the VNA to do its measurements, we need to do some either signal splitting or signal separation. And that's the job of these either directional couplers or oftentimes bridges. Okay, what they'll do is pick off a piece of the signal that's being applied to the device through port 1. That's going to be done through this receiver here called RX. So this is basically just picking off a little sample of the signal that's being applied, so that we're going to use that as a reference. And then any reflected signal coming back off of the DUT, we're going to pick that up through another directional coupler and go into another receiver. These receivers, we'll call them A, B, and R, are basically used to measure the magnitude and phase of the injected or applied signal, the portion of the signal being reflected back from the port being stimulated, and then measure the magnitude and phase of the signal coming through the device if we're looking at a 2-port device. So we've got a source, we've got some ports, we've got some directional couplers, we've got some receivers that measure the magnitude and phase of these signals, and then all of those results are collected and computed by some compute engine, okay, the microcontroller in the case of the NanoVNA, and maybe more of a computer or something like that. I do see that someone raised a hand here. Do we have an ability to answer those questions right now, or should we move on? Yeah, I don't know that any participants got a way of answering a question here. Let me just pull up the chat here real quick, if I think I can. Or I got to bring up the Q&A. Let's see. I think we're gonna have to try to answer these Q&As kind of towards the end here, if you don't mind. We'll certainly leave some time here. But certainly type in the chat if you got something urgent, and Glenn, if you wanted to interrupt me, let me know if there's something urgent that someone needs to be cleared on. Just let me know. So back to the NanoVNA. So measurements that are made on port 2 are essentially through measurements, or transmission measurements is the traditional term here. And that would be the gain or loss of the device, the the transmission coefficient, which is also called S21, or it could be S12. We'll talk a bit about that in a minute. Or things like insertion phase or group delay of the device itself. And of course, measurements made on port 1 are our reflection measurements. And these are based on the ratio of the measurements in the A receiver with respect to reference compared to B receiver with respect to reference for transmission. The reflection measurements are things like VSWR, reflection coefficient, or S11, return loss, input impedance, those types of things. Now, most professional two-port vector network analyzers will have a source and couplers on both ports. So we can measure reflections on the input and output. We can measure forward and reverse transmission. That's what these other parenthesized S parameters are. S12 and S22 are kind of the reverse measurements, if you will. But inexpensive devices like the NanoVNA are this configuration, which is often called a two-port, one-path VNA. So what's a VNA good for? So in a single port, we're making reflection measurements, and that could be a VSWR of an antenna or antenna system, could be looking at complex impedance of a device or a component, or again, looking into an antenna system or something like that. We could be looking at components. Also looking at doing things like feed line length and distance to fault. I've colored these differently because what these actually involve just a little bit more processing, often called a time domain transform in a VNA, that can actually then be used to measure a feed line length or a distance to fault. So you know how far you got to climb up the tower to find where you've got the break in the cable type of thing. The two-port measurements are transmission measurements. All right, what is the device doing as the signal goes through it? So obviously measuring things like filter shape and loss and passband ripple and these types of things, very, very useful for those of us that like building these things. Could also measure loss on a feed line, delay through a device under test, even potentially amplifier gain and frequency response. But with an inexpensive VNA like the NanoVNA, there's some precautions we've got to take there, and we'll talk a bit about that. So at the end of the day, we can measure things like antennas and duplexers and filters, inductors and capacitors, amps, splitters, balance, etc. So these are all RF devices that we can characterize with the VNA. So that's what it's good for. So another term that you'll come across is S parameters, and this can throw a lot of people because it's just kind of a foreign thing if you're not doing any real RF work. But they're really actually not that complicated. So let's break that down. Now they're called scattering parameters. I realize that probably doesn't help you understand it either. Simply, it's a ratio of a measured response to a stimulus. Okay, so in this case, the two numbers following the letter S indicate where the stimulus is being applied. So the stimulus being applied to whatever port is indicated by this number, and then is being measured to whatever port is indicated by this number. So it's the response at port X resulting from the stimulus being applied to port Y. So the response measured on port 1 based on the stimulus being applied to port 1, for example, that would be S11. So it's basically the ratio of that A receiver divided by the reference. Okay, so that's the reflection from a DUT at a port. The transmission through a device, we're measuring in the B receiver up here. Okay, so the S21, it's the response at port 2 with response to the stimulus being applied at port 1. So that's where the 2-1 comes from. Again, that is the response through a DUT, things like insertion loss, delay, things like that. So another thing that can confuse people a lot is like, well, I've got all these other analyzers and I've got my multimeters and all these things. I don't have to run a calibration on them all the time. Why do I have to calibrate a VNA all the time? Okay. And what we have is something actually called a user calibration. So why do we actually need it? Well, number one is a VNA, by its very nature, kind of like spectrum analyzers, have a very large measurement dynamic range. So even small errors and small nonlinearities can affect the measurement, because I might be measuring, I might have 60 dB or more of dynamic range in the measurement. So it's something that, any little change in cable and connector can often change things. Another reason we do this is because we're measuring phase. Now, phase, as you know, is just another way of thinking about delay. Okay, so if I add a piece of cable or a connection between my measurement device and my device that I'm testing, maybe I'm testing a filter, and I've got a cable going between them. If I'm measuring, say, the reflection off of the input of that filter, okay, the phase of that signal being measured at my measurement instrument is going to be affected by the amount of delay that I have in the interconnection to my device. So I've got to be able to take that out of the measurement, because that's not part of the phase response of my device. That's just due to the interconnect, right? It's getting there and getting back. So it's called establishing a measurement plane. So if we want to measure an accurate phase measurement, and we want to ensure that the reflected signal coming back that's due to any of the instrumentation is not part of the actual measurement that we make. So this is all part of establishing a measurement plane, so the measurements we make are right at our device port and not at the VNA's port, for example. We'll talk a little bit more about that too. Now, of course, a factory calibration can't account for all these things, because the factory doesn't know what you're going to be testing, how you're going to be connecting up to it, what your fixtures look like, or anything like that. So this is why we want to do a user calibration. And we want to do it whenever there is a configuration change, whether we're setting a new cable, a new fixture, a new adapter to get to the device I'm measuring, and certainly if I'm making a change in the frequency range that I'm making measurements on. Because when you run a calibration, you're measuring it over a finite number of points between a start and stop frequency. And if you test over a different range, you didn't calibrate at the points that you're actually measuring. We'll talk, and some VNAs we'll talk about will actually interpolate between those points, but some don't. So it's important to recalibrate when you change the frequency range you're measuring over, in most cases. So what does a user calibration actually do? It corrects for something that we call systematic errors. And these are errors that are relatively predictable and aren't going to change while you're making your measurements. So it's not things like drift, but it's things such as what are called tracking errors, which are the source and receiver frequency response. So the frequency response of the source going out, the couplers and directional couplers and things like that, or bridges, and just zeroing that stuff out. So that takes into account the instrument capabilities. Also, any mismatches at the ports, they're going to cause reflections of their own. We want to be able to remove those from our measurements, so we're only looking at the measurements from our device. And then also the directional couplers and things like that, and bridges and things like that are not going to be perfect. So they're going to have a certain amount of directivity, meaning signals going from the direction other than where we intend to sample them are going to leak through. So that's one measurement, that's a measure of directivity. And also there may be some crosstalk between the ports, basically signals that bypass the DUT. We want to be able to account for all of that so we can remove that from the measurement itself. And of course, finally, as we mentioned, we want to essentially remove the effect of any user applied cables and fixtures up to our DUT. So we establish that measurement plane right at the DUT's ports. So this is what a user calibration actually corrects for. Okay, by making the various measurements, it can mathematically remove these sources of error. So in a VNA, most of the measurements that we make are made versus frequency. And they could be reflection coefficient, or S11 measurements, or S22 in the case of a two-port VNA. And most commonly, the display you're going to look at is a log magnitude display of that reflection coefficient. And mathematically, that's certainly related to a VSWR. The VSWR is typically going to be shown in a linear type fashion, 1.5 to 1, et cetera, however it might be. Okay. Also, we can measure complex impedance. The most common way of visualizing that is on a Smith chart. probably, well, we could talk a little bit about the Smith charts. I've actually got a number of videos on that, and it's a topic for a whole nother presentation, but we'll certainly cover some of the basics. The transmission coefficient, okay, and this could be insertion loss and insertion gain, or in S parameter parlance, it's S21. And again, oftentimes we're going to view that as log magnitude. You know, in some cases, you may need to know about the phase of these two, and we can view that as well. But most of the time, we're just looking at the log magnitude of the reflection and transmission coefficients. Again, things like insertion phase, delay, group delay, these are typically linear measurements as well versus frequency. As I mentioned, there's a time domain transform in many VNAs, including the NanoVNA, that actually makes the measurements versus time and can be converted to distance to essentially, again, measure the length of a hunk of coax or a distance to fault in a piece of coax or something like that. And it's often helpful, even though the transform will use the reflection coefficient typically as its metric, it's often helpful to change the format to linear because you'll get a sharper peak in the result as opposed to a bit more rounded peak, and it might give you a more precise measurement of where a particular defect is in a hunk of coax. Okay. So with all that basics of the VNA under our belt here, let's talk about the NanoVNA. Okay. Now, of course, there are several variants and developers. The NanoVNA originally appeared in as a GitHub project several years ago, and was picked up by a couple of folks that started to make some variants of their own. One of the original ones that were kind of somewhat commercialized is a guy named Hugan or Eddie55. There's a couple of different guys out there, and the original version is kind of designated with this letter H, like a NanoVNA H. And it came out with a 2.8-inch display. Initially came out without an enclosure, and was kind of out there. And a lot of people started cloning that right away, but it was available, and again, inexpensive, $50–$60. This guy who goes by the letter H also developed a 4-inch version of it, a 4-inch display with a pretty nice extruded plastic enclosure. And this is probably one of the more popular ones that's out there. It's the one that I have. I don't know if you're looking at my webcam, but that's the one that I have here as well. There's the NanoVNA H4. Okay, and there's also another 4-inch version that's a -F. A separate developer took the idea of the NanoVNA. He actually made some hardware changes to it. Doesn't go quite up as high in frequency. It's a little more expensive, but it has a really nice aluminum case. So if you want something a bit more rugged, that's a nice one. And also the guy who did the F version corrected one of the things that one of the little pet peeves that I have is that just about the entire VNA world will call the two ports on a 2-port VNA, port 1 and port 2. For some reason, the NanoVNA, it's called channel 0 and channel 1. This just adds to the confusion. So the guy who developed the F version, he calls them properly port 1 and port 2. He did a couple of things. He added actually a scale to the display. So it's actually a nice unit. It's a little bit harder to find, a little bit more expensive, but it is another 4-inch version that's out there. Not the same firmware, but virtually the same usage and operation. But the firmware is not interchangeable between these two. Now there's a version 2 that's has been developed during kind of the early part of this year, and it's got this very unfortunate name, SAA2. This guy will go up to 3 gigahertz of frequency range, and again, initially come out without any kind of a case, and we're starting to see some available with cases now. And as of when I put this presentation together, I kind of like the H4. It's the one that I have. It's easy to get. Performance is certainly good enough for most everything that most us amateurs want to go and apply it for. And it's got some pretty good support. There's a number of folks that are doing enhancements to the firmware and things like that. So I kind of like it. The V2 does have better performance, okay, and has a higher frequency range. Again, goes up to 3 gig, whereas the H4 goes up to 1.5 gig. But it only has a 2.8-inch display, and again, didn't really have a case. I just heard actually about a week ago, or a week or two ago, that they started selling a 4-inch version with end connectors, and I think it's in a case. But cost a little over $100. But haven't really, it's not as popular and easy to find yet as, you know, some like the H4 is, for example. So it's because there's not like one manufacturer for these things, and there's clones that are popping up and things like that. It's kind of a moving target in terms of where everything is. So you almost have to kind of do your research online to see what's there, or purchase from kind of a known trusted vendor in terms of to ensure you get a decent unit that was built with proper shields and that type of thing. A couple more details. This is kind of how it looks when you purchase it from one of these kind of more reputable dealers. Comes in a nice little box with a molded insert. All of these NanoVNAs are 2-port 1-path, meaning they've got, you know, 2 ports obviously, but they only have one signal path, meaning they've got one source that comes out of one port and that can be used for the reflection measurements and the transmission measurements. The H4, as I mentioned, goes up to 1.5 gigahertz. They offer standalone operation as a built-in battery, so it'll operate for a few hours to standalone. It does have a USB port on it, so it's how you charge the unit, but it also can be used with external software. One of the more popular PC-based software packages is called the NanoVNA Saver, but there are other variants out there, and we're not going to talk about them in today's presentation just due to lack of time and the fact that I haven't really played with them either. To me, I like the fact that it's portable and I can just bring it on the bench. I don't have to be tethered to a computer somewhere. But if you're making some real measurements, you want to document things, and there's some other advantages that the software brings that might be important to what you're doing. There's a pretty good well, this is the kind of the web page for the NanoVNA. It's actually a pretty sparse page. This is kind of what you get when you get to that page, and it's a lot of it's just kind of wiki-based information. But you'll find, you know, some links to the Saver application, the menu structures, a whole wiki that kind of goes through the history of all the different variants of things like that. So it does require sometimes a little bit of homework and research if you want to really understand what you're looking at here, and to see where they're going, because again, it's not like one manufacturer that's providing these things. It's not like buying something that's made by Rig Expert, right? There's a couple of developers and a couple of different variations. So under the hood, what's in there? It's actually a pretty simple device. So we've got, here's our channel 0 and channel 1, okay, our transmit and receive port, okay? So this is essentially port 1 and port 2 are there and there. This is our RF source. How many times over the past 2 days do we hear people talk about the SI5351, you know, microcontroller controlled synthesizer? That's what's used inside the NanoVNA. Okay, nice thing is it has multiple outputs. Okay, so we can supply, you know, one output to, it's actually a bridge that's used instead of a directional coupler for the signal that's going out to channel 0. But then there's actually a so you can see this is, we've got the mixers here. Again, another familiar device we've talked about a couple of times this weekend, the SA612. Those are the mixers that are used for the reflected signals. This is our A receiver effectively, and this is our reference or R receiver, and then our B receiver on port 2 right here. So those are all the mixers there. All of the LOs for those mixers are all coming from the SI5351 as well. And then all of the analog to digital conversion is actually done in this stereo audio codec chip that is typically used in, you know, mobile audio devices and things like that, but is a very high volume chip that was very inexpensive. It's got some really nice, you know, high resolution analog to digital converters in the audio range. So essentially we're converting using the 612s down to audio frequencies, and that's all being sampled by this stereo audio codec. And then all of that is being controlled by a microcontroller. In the case of the NanoVNA, it's this STM32. Okay, and that controls the SI5351 and takes all of the sampled data from the codec and does all of the other measurements that are put up and controlled up onto the LCD. And then we just have a USB interface, some user interface controls here, and power supply and battery charging system. So that's the block diagram of it. This is actually the schematic of the H4 that I have. I'm not going to go through it in detail, but just to point out, there's where the channel 0 bridge is right here. You can recognize the structure of the bridge. There's an attenuation pad that's used to improve the input return loss of channel 1 or port 2. The RF source right there is our SI5351 here. Here's all of our mixers. Those are the SA612s, the audio codec chip, the microcontroller, the USB and battery charger, voltage regulator, all right here. And then we've got the connections for the LCD display and things like that over here. So what's the user interface look like on the NanoVNA? Because if you look at it, you first turn it on, it's like, boy, that looks complicated. Everything is laying on top of each other. And that's one of the downsides, is that there's a number of different displays that are all laid on top of each other. And until you're familiar with what those displays are, it can be really confusing. So how you drive this thing? There's an on-off switch over here. And then there's this jog wheel. Heather mentioned this yesterday during her talk. It basically has got a couple of functions where you can push it in or out to make selections, and rock it back and forth to scroll back and forth between selections in a menu, or to move a marker, for example. But it's also a touch screen. And the touch screen is a typical tap and touch on the touch screen, but you can also tap and slide. For example, if I wanted to drag this marker to a different spot, I can touch on it and drag it to a different spot. So a couple of ways of driving it. Obviously a lot harder to do on the 2.8 inch display. It's a little bit easier to do on the 4-inch display, the H4 or the -F version. That's a fairly simple menu structure. All the menus will pop up here on the right-hand side. And the home menu, the top menu, is shown here. You've got displays to control the traces, the channels, what format, the scale, all that all through the display and its sub-menus. You can add markers with the marker menu. You control the frequency range you're making the measurements over using the stimulus measurement menu, and then the calibration menu, etc. Okay. When you do a calibration on the instrument, you actually have got 5 save slots that you can save the information into. And not only does it save the calibration information, but it also saves the configuration. What displays you have turned on, what traces you have turned on, what frequency range you're using, etc. So if there's things that you're doing more often, maybe you're building a couple of filters, a couple of different IF frequencies and things like that for your rigs, you can do a couple of calibrations over certain frequency ranges, store them to certain slots, and then each time you go to build a new filter, just recall that particular slot, and you don't have to redo a calibration again. Okay. Now, obviously, there's a USB charging and PC interface on it. On the H version is sitting right down here in the middle on the edge of the case. So we mentioned calibration a couple of times, so let's talk about what this is and how we go ahead and do it. Now, one of the downsides with the NanoVNA, the H and the H4, is that it only does 101 points across the sweep. Okay, so if you do a wide range calibration, like when the default calibration when you first get the unit is from 50 kilohertz to 900 megahertz, the spacing between each of those calibration points is going to be whatever that span is, frequency span is, divided by 101. So if I use that default calibration of 900 meg calibration, I've got about 9 megahertz between each point that I've calibrated. So, I mean, that'll skip right over. If I want to do some measurements on the 40 meter band, I might have 1 point in that 350 megahertz, 40 meter band. So, hence you want to redo calibrations. And as I mentioned, many VNAs, including the H4, will interpolate between the calibrated points. But if you got a huge spacing, the validity of that interpolation might be in question. The newer version that I mentioned, the SAA2, does not interpolate between calibrated points. So you're not going to get a calibration unless you calibrate over the frequency range you're measuring over. Okay, so like I said, most will interpolate between the points. But it's always a good idea to calibrate over the frequency range that you're measuring. Okay. So, and how you can tell the instrument is calibrated or not is actually with this set of letters over on the left-hand margin of the display. So the first line, the capital C, means that I am calibrated for the current frequency range that I'm measuring. Okay, so the calibration was last done over the same start and stop frequency that I'm actually making my measurement over. If I change my measurement frequency, that capital C will go to a small c. It means that I've got a calibration that includes this frequency range, but doesn't match the specific range, which means I'm going to be doing some interpolation between the points. The number following the C indicates where the current calibration is stored. The most recent calibration, the one that's being used and applied, that's showing me what slot that was pulled from. Again, by default, when you power up the instrument, it'll recall the contents of slot 0. So if you have a common thing you do all the time, do a calibration stored in slot 0, then when you turn it on, you don't even have to recall anything, you're good to go. Okay. The next letters, D, R, and S, refer to the directivity error correction has been applied. So I've done the calibration so that those directivity errors that I mentioned earlier are being applied. The R means that the reflection tracking errors have been applied, and the S means that the source match errors have been applied. Okay. And then the last two, the T and the X, refer to transmission tracking error has been applied and the crosstalk error has been applied. Okay, so those first three are really required for all the measurements, whether you're doing reflection measurements or transmission measurements. You really need to have those done. And this is all just part of the calibration process. These things will light up. And if you're doing transmission measurements, making a two-port measurement, then you'll need these other two. There are two steps that you do to create these correction coefficients. If you're not going to be making a two-port measurement, you can even ignore that portion of the calibration step, and the T and the X won't appear there. Okay. So here's the process. Again, because it's one of those things that I've got a video on this, but we'll just summarize it here in a slide or two. Starting from the main menu here, we hit Cal, and the first thing you want to do is hit Reset to reset and clear out the calibration the corrections that are currently in there. So once you hit the reset, once you hit that reset, sometimes you might want to hit it once or twice even. Some people say you have to hit it twice. I don't think you do. I think the first time actually turns the corrections off. The second time actually clears the little letters on the left side of the display. Once you reset it, then we're going to actually go and start the calibration process by hitting Calibrate. Once you hit Calibrate, the menu changes to this menu here. And this is just a process you're starting from the top and working your way down to the bottom. You apply an open to channel 0, okay, and hit open. This once it makes the measurement there, the open text will go to inverse text, kind of like correction is shown here. Once that's done, you then apply the short to channel 0 and tap on short, and then apply the load 50 ohm load to channel 0 and hit load. So you've got all three of those. All three of those will then show as inverse text. And again, those are the only ones you need to do if you want to make just reflection measurements, but they are required for both reflection and transmission. If you're going to be making some transmission measurements, measuring a diplexer, measuring a filter, then you have to do the next two steps, which are the isolation and through. For the isolation step, you just want to terminate channel 1. Put the 50 ohm terminator on channel 1, hit isolation, and then you connect, then you could pull that off and then connect channel 0 to channel 1 and do the through measurement. Again, you only need to do those if you're actually making a two-port measurement. Once you've done that, then you hit done, and the next menu will pop up, will allow you to ask you what slot you want to save that result into. So again, slot 0 will be recalled on power up, but then you've got 4 other slots available to you. Now, ideally, and we're going to talk about this here in a minute or two, all the connections of these Cal standards really you want to make those measurements right where your device is actually going to be measured. Okay, and so that will take into account and essentially remove the delays of the coax and any other interconnects that you have going up to your DUT. Okay, to establish that proper measurement plane. So let's talk about that calibration plane and port extension. So I've got my NanoVNA here, I've got my DUT. When I go to do my measurements, I ideally want to take the connection off of my DUT and go right to my cal standard. Ideally, that's what you want to do. Sometimes you can't do that because of interface, different genders of interfaces, or maybe there isn't a connector on your device, or you got to solder something down. So sometimes it's not possible, but ideally that's what you want to do, so that you're calibrating right to your DUT. So when we measure phase, it's phase at the DUT port, not phase as measured through the cable. Again, this removes the phase of the DUT from the ports. But now, if you must use an adapter or coax or a fixture, or maybe you got a PCB trace, or you're soldering something down, and where your cal standards are applied are not the same place where your DUT begins, you can use something called a port extension. And I've got a video on this as well. But what the port extension does is says, well, okay, I'm making a measurement, here, but I had to calibrate here. I know the delay from here to here, and I know that's a good consistent 50 ohm environment. So as long as those kind of hold true, you can apply this port extension. Now, unfortunately, the NanoVNA doesn't call it port extension. They call it electrical delay. Okay, and what you do is you would, if you actually want to apply this, you would apply a short or an open at your DUT. And like for example, if you were soldering down to a board here, maybe you just momentarily solder bridge it to create a short, or disconnect a component to create an open. And on the Smith chart, that would normally appear, if it's an open, would be all the way over the 3 o'clock position. If it's a short, it's all the way over at the 9 o'clock position. But if I have an additional delay due to a cable, that's going to cause some rotation on the Smith chart. So by adjusting the electrical delay and moving that point and just observing it on the display until it goes back to the open or short, okay, whichever you've got applied, then you've effectively added the appropriate amount of delay to account for that additional, or either additional or attraction of the interconnect between where we were calibrated and now where the DUT actually begins. And again, it's really important when you must have an accurate phase measurement at the DUT. That's really where it's most important. If you don't really care about that, you're just doing log magnitude, you can generally get away with it. Depending on how much delay, you might get a little bit more ripple in the passband result or something like that, but it's not a huge deal. Okay, but that's what port extension is. So let's talk about a little bit more on the interface. The NanoVNA, again, has got channels, channel 0 and channel 1, right? Channel 0 is for all of our reflection measurements, for S11 or reflection coefficient, VSWR, input impedance, again, distance to fault with the transforms. Channel 1 is the transmission measurement, insertion gain and loss, group delay, that type of a thing. Okay, so that's going through display, channel, select channel 1 or channel 2. The traces, you have up to 4 different traces available to you. Those traces can be assigned to any channel. So the way you would do it is say, okay, I've got trace numbers, trace 0, I want that to be SWR. So you'd select trace 0. When a particular trace is selected, its indicator on the display goes to inverse text, so you'll know that's being selected, and then you can go down and tell it what channel you want that trace to be. Okay. By default, when you first power the unit on, there are 4 traces turned on. 2 of them are on channel 0, 2 of them are on channel 1. You might say, well, I want all 4 of them to be on channel 0. You have to go and select each trace and tell it which channel you want it to be on, whether you want it to be a reflection measurement or a transmission measurement. Now, each trace can have a different format, okay, depending on what you're measuring. Okay, so channel 0, again, typically, if you're doing the log mag is actually the S11 parameter, or the reflection coefficient. That can be displayed in linear or log mag, but mostly it's log mag. The Smith format is primarily for looking at complex impedance and how that impedance is changing versus frequency. SWR, obviously, we all know what that is, looking at standing wave ratio. These are all different measurements that can be made essentially on channel 0. And then the channel 1 are the phase and delay measurements, as well as log mag for the insertion loss or insertion gain. Okay, you certainly could apply a format to a trace that doesn't make sense, but you just have to kind of know what you're doing here. Okay. There are some other formats as well that may be useful. As I mentioned, the linear format is typically used when you're doing SWR. Polar format might be useful for folks that want to look at a complex value in a polar diagram. Real or imaginary if you just want to pull out the particular components of a complex measurement. So a couple of other things you can actually bring up here, but these are the most common ones that you'll use up here. Now, when you make the measurements, you have to set what frequency range you want to make the measurements over, and that's using the stimulus menu. Okay, so and you can pick whichever is easier. It might be easier for you to pick the start and stop frequency that you want to make measurements over. So I bring up the main menu, go to stimulus, go to start, hit start. It'll bring up a numeric keypad. You put that in, then you hit enter. Go back and select stop. Same thing. Okay. With the menu structure, you only have one menu up at a time. If you don't have a back down on the bottom, like this guy right here, that means you're at the top menu. If you see back, that means you're not at the top menu. So that's an easy way to navigate back to the top menu is just keep hitting back until you don't have it anymore. Now, in some cases, it might be easier for you to pick a center frequency and a span, right? If I'm measuring an antenna, I might want to set a start and stop frequency. If I'm measuring a filter, I might say, I know my filter center frequency is X, and I want to measure a span of Y around that. So it might be easier for you to enter a span. Those are just two alternate ways of entering the frequency range you want to make your measurement over. And if you want to make measurements at a single frequency, you just select CW, and then it won't sweep. It'll just output a constant frequency at that frequency that you asked for. Okay. Now, the NanoVNA has got 4 markers that are available to you. They're the little triangles that show up on the traces. Okay. Again, the values of where the marker is show up on the display here. So if we read this top of this display, I can see the yellow trace is it's on channel 0, so it's a reflection measurement. It's the log mag, so it's a log magnitude of S11. The vertical scale is 10 dB per division. And where this marker is, I'm at minus 8.19 dB. Okay. And the markers will track each other in frequency across all the different traces. Okay, so the selected marker that we're actually controlling, we can scroll it back and forth with the scroll wheel, for example. The selected marker is going to be shown here. So I can see the selected marker is marker number 2. That shows number 2. And this shows the frequency that marker is sitting at. It's sitting right now at 360 megahertz. Okay. If we have more than one marker up, you'll get a second line here. And the second line will show the delta between the current marker and the last one that was a current marker. So in this case, I had selected and adjusted channel marker number 1 first, then I made marker 2 the active marker, so I get a delta to marker number 1. So this might be helpful to look at, maybe loss in a filter between, say, the passband and how many certain number of dB down to make a measurement of bandwidth, for example, because you might have some insertion loss. All right, so you can put the one marker on the passband, read the insertion loss, a second marker 3 dB down from that on either side to figure out what the bandwidth is, for example. Okay. Again, they all track each other in frequency, so when you move, just moving the jog wheel back and forth will actually move the marker back and forth in frequency. They all track each other. There are search features. You can search for min and max, or you can just search for the next min or the next max left and right. Okay, that's what the search features do. And there's operations you can apply with the markers. And that you can, for example, I can move a marker and then tell it I want the start frequency or stop frequency or the center or the span to be defined by what the markers are. So you might see an interesting frequency range and then change your start and stop frequency based on that. Okay. And of course, the Smith value tells you how you want to read the Smith chart units off of the Smith chart trace, whether you want that to be complex impedance or whatever it might be. Okay, so here's what's the process of actually setting up and using the VNA? Generally, what I do is I start off by configuring what traces, channels, and formats I want, right? Because usually when you power it up, it's not exactly what you want. So I say, maybe I want to have 2 traces. I want to have SWR and S11. I'll turn the other 2 traces off. Or if I want to measure just the insertion loss of a filter, right? Maybe I don't need the Smith chart. I just want to look at S21. So pick which traces, channels, and formats you want. and then set the stimulus, set the frequency range you want to make the measurements over. Of course, you can do those in any order. You don't really have to do one versus the other. The instrument doesn't really care, right? So, but bottom line is you get the stimulus, traces, channels, and formats set up the way you want. Remove all the unnecessary stuff and noise that's in your way. If you don't want the Smith chart, just turn that trace off or assign that trace to a different format. Then you do the calibrate. Okay, you calibrate it and save. And it really is, again, it's a pretty simple process. It literally takes 30 seconds, so it's not a big deal. Just have those little standards available and do the calibration, and then save it off. Again, save it into slot 0 if you want to recall it at power up, or save it into another slot number. Unfortunately, you can't rename those slot numbers. So if you have a number of them you're going to use more often, you might have to make yourself up a little cheat sheet of what which one's which. And then you connect your device under test and do your tests. And use your markers, move the markers around, make the measurements you want to do, maybe even adjust the traces and formats as needed. I might want to change how I'm measuring things, change a scale or something like that. But the first 3 steps here are really the most important thing in terms of getting set up. Okay. So here's an example of what it might look like to measure an antenna. Okay. So in this case, I've only got 3 traces turned on. You can see I've got channel, and they're all on channel 0. So this yellow trace is looking at the log magnitude of the reflection coefficient, okay, or S11 on a 10 dB per division scale. The green trace is looking at the Smith chart, which is showing me the complex impedance, and that's the circular scale, these little circular arcs and things like that, showing me complex impedance versus frequency. And then the cyan trace is showing me SWR. There's the SWR trace. And the scale is 1 per. So this would be 1 to 1, 2 to 1, 3 to 1, 4 to 1, etc. Okay. So there's the VSWR trace. Okay. Again, that's this blue trace, the complex impedance, the Smith chart trace, and the reflection coefficient. And of course, you can see the reflection coefficient dip and the minimum and the SWR happen at the same place. These are simply mathematically related. Sometimes it's easier to pick out a resonant frequency by looking at the reflection coefficient because because of the log magnitude display, it gives you a much sharper note. And this can be really handy when you're looking at things like duplexers and things like that. It's a lot easier to pick out a resonant point by looking at the S11 versus looking at SWR. So how about measuring a filter? Okay, so the filter would connect up between channel 0 and channel 1, or port 1, port 2. Okay, in our case here, here's the frequency range. In this case, it's a 1 meg to 15 megahertz filter. This is actually the filter that I used when joining the Color Burst Brigade and made my little Michigan Mighty Mite transmitter. This is the low pass filter that I followed the Michigan Mighty Mite with on 80 meters. So we've got the insertion loss, right? So you can see that's channel 1. So that's actually a transmission measurement. So that's the log magnitude of the transmission through that filter. So I can see at 1 megahertz, it was nearly 0 dB, which is good. And then I went make the measurement all the way up to 15 meg here. So we can actually see that we're about 10 dB down right about here, and we can move markers back and forth. This marker right here, we can see, is sitting at 10.5 megahertz. Okay, so that's near the 3rd harmonic or so, and that's 47 dB down from 0. Okay, so that gives me an idea of the insertion loss at the third-ish harmonic of my Michigan Mite, or the filter that's being applied to the Michigan Mighty Mite. The reflection coefficient, this shows me the input match looking into the filter. So that's better than 10 dB down. Okay, so it looks pretty good. So I'm not going to get a lot of reflection off the input of the filter. Out of band signals are reflected away from the filter. That's part of how it's doing its attenuation. It's just not letting those things through. Rather than absorbing them, it's actually reflecting them back. And that you can see that in the reflection coefficient. You can also see it in the SWR plot here. Right? The SWR rockets all the way up here as we get past the corner frequency, causing those higher order harmonics of my Michigan Mighty Mite to be reflected rather than transmitted. And then the input impedance, I really didn't have to have this trace on here, but I do have, it just kind of shows the input impedance is near the center, at the beginning of the frequency range, which is where we are here. And then as you get away from go higher in frequency, we're getting, looking actually more and more capacitive, as that's what that filter looks like at that point. So. And we want to measure the length of a coax. This uses this time domain transform, so it's a different format. And the axis now becomes a time domain axis. Okay. Again, it's helpful to use the linear format here. It gives you a nice sharp result here. And this, you pick a frequency range, and the frequency range you pick is going to help determine what distance range you can measure. And again, I've got a video on this one as well, so you could take a look at that to get a bit more detail on that. But it at least gives you a way now of, in this case, measuring where I'm getting, at what time domain or time delay am I getting a discontinuity. And with the marker, that will actually get converted to distance. In order to convert that properly, you have to tell the NanoVNA what the velocity factor is of the coax. And there's a spot you can enter that in as well. So that's how you would actually just measure distance to fault or the length of coax. Okay. Now, of course, you can change the display format again, not use the transform, connect up both ends to from channel 1 to channel 2, and measure the insertion loss of the coax as well. Again, very similar to measuring a filter, but you can't do both of those at the same time. So you're going to be doing a transform or not. Okay. So what are some of the limitations and downsides? And I call this the good, the bad, and the ugly. Okay. What do we like about it? What don't we like about it? Right. We talked a lot about what we like about the NanoVNA. Number one, it's cheap. We're hams. We like cheap. Okay. And it's got a lot of capability. Okay. But what's one big limitation? 101 trace points. So you don't get a lot of resolution if you're trying to measure a multi-band antenna. You're not going to get a lot of resolution on each band. But also it does affect the ability to, when you do your calibration, you got to make sure you've got calibration points that really lie within the frequency range you're measuring. Now, the external software that we mentioned, like NanoVNA Saver, that can help with this because you can actually have more trace points with the external software. It actually measures in multiple segments, so you can get better resolution in terms of time or frequency resolution in those measurements. The output is a square wave. It's not an RF source. Right? The output of the SI5351 is essentially a square wave. In the case of the H4, it's about a 600 millivolt peak-to-peak square wave. That's what it looks like. Okay, and it only goes up to 300 megahertz. So when we make measurements from 300 to 900 meg, it uses the third harmonic of that. If we measure from 900 meg to 1.5 gig, it uses the fifth harmonic. So this output that I'm showing here is a 200 megahertz square wave. It's exactly the same output you're going to get the device if you measured at 600 meg, and it's exactly the same output you get from the device if you make a measurement at 1 gigahertz. Okay, so you have to keep that in mind. Depending on what you're measuring, if you're looking at something that's a broadband device or might be affected strongly by an out-of-band signal, keep that in mind that you're going to have the output is rich in odd order harmonics. This is the spectral content of this signal. So there's my fundamental at 200 meg. There's my third harmonic at 600 meg. There's my fifth harmonic at 1 gig. Okay, so they're all, and you can see that they're all pretty strong. I mean, the second harmonic is only about 10 dB down. The third harmonic is about 20. And speaking of power, the output power is not adjustable. From 50 kilohertz to 300 meg, you have about this 600 millivolt peak-to-peak square wave, and you have about, it varies between like 0 and plus 2 dBm. Again, this is for the H4. Some of the other versions might be a little bit different. And the third harmonic that's used from 300 meg to 900 meg, the output power is minus 8 to minus 12 dBm. And then the fifth harmonic for the measurements made between 900 and 1.5 gig, the output's between about minus 17 to minus 24 dBm, not adjustable. So that means is you have to think about, depending on the device you're testing, is that output power appropriate for that? If you're measuring an amplifier or a preamp or something like that, it might not be appropriate. It might be too much, it might be too little. The fact that you've got all these harmonics and it's a square wave might be an issue. But it also means you can't do measurements such as gain compression measurements, which is also a common thing with most VNAs, where you vary the input power and measure the output power and determine when the gain goes down by a dB, right? That's like a 1 dB gain compression measurement. You can't do that with the NanoVNA, okay? Fixed output, square wave, all it does is change in frequency. Okay, so keep that in mind. A little bit more of the ugly here. Another piece of the ugly is that input signal level, reference level to the receive port, channel 1 port, is not adjustable. There's no input attenuator there. There's a fixed attenuator and that's it. You can't adjust it. So this might be an issue if you're trying to measure an amplifier, for example. Okay, you might have too much signal going in and overload the instrument, or you might not have enough. You can't adjust the reference level at the input. You may have to use some attenuators on the outside to kind of get reference levels where you need them to be. Okay, so it's from a VNA standpoint, from a professional VNA standpoint, it's relatively limited in dynamic range. The dynamic range over the first 300 meg is actually pretty good. It's better than 60 dB or better. But you get up to using the harmonic levels, and even at 1.5 gig, you're lucky if you get 35, 40 dB dynamic range, if that. So again, compared to more professional instruments, it's limited in dynamic range, but still pretty good for a $60 device. The resolution bandwidth in the results, since we're measuring signals over frequency, the resolution bandwidth is not adjustable. It's in the it's in the single-digit kilohertz range, I think, 5 to 10 kilohertz frequency range in terms of the resolution bandwidth. What that affects is how low the noise floor is on the measurement. Okay, but it is not adjustable on the H4 and the F version. I think the F might actually have an adjustable RBW. Certainly there may be other limitations, but these are kind of the biggest limitations compared to kind of a traditional, or a more professional VNA. But most of these we can just overlook because they don't matter that much for the things that we're going to do most often, which are probably looking at antennas, looking at things like homebrew filters and things like that, and maybe looking at some coax issues. Most of these things we can forgive. So in summary, the NanoVNA is kind of the RF tool or toy of the year. I think Heather said that yesterday, and I kind of agree. Really amazing capability for about $60 US. There's tons of videos and things like that out there, not only on my channel, but in other places. It's a very, very active user and support group. A good source in the US for these units, where they're sourcing them from legitimate sources that are not cheap knockoff clones, is R&L Electronics. You probably have got a similar source you can trust in the UK. So with that, I appreciate the time here. I'm not sure how we're doing on time actually, but let's see. We've got some time, I think, here for some questions.
Yeah, we're good on time. We have at this point 9 questions in the Q&A.
Okay.
Can you bring up the Q&A?
I can. Yep. Yeah. So let's take a look here.
I have found the best way to do this is to have you answer from the Q&A because it's answered faster.
I could do that. Okay. So I'll read the questions here for those that can't pull it up. So the first is from Marv NV3V. It says, I have an interesting use case for the NanoVNA test. I have one, and I'm about to analyze a gutter to be used as an antenna, a gutter on the house. Its behavior before I build a 9-to-1 balun or use a tuner. I just want to see the Smith chart to identify the impedance presented to any device I attach to the gutter. Hey, great use case for it. So just keep in mind that the NanoVNA is designed primarily to be a 50 ohm instrument. So if you're expecting other system impedances, just keep that in mind. But certainly, I think that's a great way to go look at it. And if you got a feed line connected up to a balun or up to the gutter on the house, really what's important is what's the impedance looking into that feed line, right? You can use port extension and things like that, or if you can remotely calibrate to the end of the feed line where you're going to connect up to your balun, you could actually use port extension to get there. If you wanted to build a more proper matching network at the outside of the house instead of the input of the gutter, you could do that. But certainly that's a cool use case. Let's see, can you use S2 to measure harmonics on a transmitted signal with the appropriate attenuation of the transmitted signal? The answer is maybe. The reason I say maybe is that if I use the second port essentially as a spectrum analyzer is what you're really asking. Obviously, you've got to limit the input power to probably 0 dBm or less. And you probably will have to keep readjusting the measurement frequency because we've got only 101 points and a relatively narrow fixed resolution bandwidth. There's a possibility that the harmonic might land outside of the frequency range that the resolution bandwidth covers, and you'll miss something. So it's not really a good spectrum analyzer, but if you play with it enough, you might be able to at least get something somewhat reasonable. But again, you definitely got to attenuate, and then just keep in mind that you've got a relatively narrow measurement bandwidth, and you've got a fairly coarse 101 point spacing. So if your signal of interest lies between those 2 points and you're not within a few kilohertz of those points, you may miss the signal. I hope that answers your question, Mike. The next, another question from Marv. I'd like to learn how to actually measure a balun. It's a really good question. It's something I've actually gotten a number of questions on that, and I plan on doing a video on that in the future, but haven't gotten there yet. Probably more that we can answer, probably a bigger answer than we can answer right here. So I would just say stay tuned for a future video. Unfortunately, got to put that one off that way. Next question from Dean, KK4DAS. What's the purpose or advantage of the very expensive professional calibration standards? Why are they so expensive? Is there any advantage to our common ham apps? I think for our common applications, there really probably is not much of an advantage, because the advantage to these very expensive cal standards is that not only are they very precisely, a very precise 50 ohm, but also these cal standards, when you get up to the millimeter wave and microwave frequency range, an open or a short is not just simply 0 ohms and an open. There are other parameters, fringing capacitance and things like that, that affect the impedance of those opens and shorts to establish the measurement plane. Those are are very accurately characterized on these expensive cal standards, and they're also put into as a reference into the analyzer itself to be able to use that, because the points that we're essentially targeting on the Smith chart aren't exactly at the 9 o'clock and 3 o'clock position in reality. But for our inexpensive cases, we're just targeting the kind of the center of the Smith chart and the 9 o'clock and 3 o'clock positions. The other thing that makes the professional cal standards more expensive is that they're very precise mechanically. So that there's some really tight tolerances involved with the connectors themselves that make sure that they're very consistent every time they're used. Again, in order to achieve 100 dB or better dynamic range and things like that in the measurements, you need that type of thing. For our hobbyist use, it's not worth the extra money for those things. Let's see. Let me see if did I miss a question here? Or they're coming up in a weird order here, so I got to keep scrolling back. So there was a question here from Bal, EA8BVP. Thank you for your talk. Thank you. Can I measure an antenna VSWR if the NanoVNA is using ladder line? Again, the NanoVNA, well, it's still going to show you the input impedance looking into that ladder line. Okay, so you may have to just solder up an adapter to get in there. It's still going to show you the impedance, and if you're using the ladder line as part of an impedance transformer, or if you're going to put a balun on it or something like that, you can certainly do that, because the input impedance, if the antenna is not matched to the ladder line, the impedance looking into the ladder line is going to depend on frequency and line length. So it could be anything, right? So certainly it's still going to show you that impedance, so you certainly can do that. Again, just keep in mind you're going to have to fashion a way of making the connection, and then keep in mind that you may have some other issues with what impedance it is. The problem with the NanoVNA and most VNAs is that they're designed to be around a given system impedance, in this case 50 ohms, and they're not too bad in terms of accuracy, an order of magnitude one way or the other, like down from like say 5 ohms to 500 ohms. Once you get too far beyond that, then the accuracy starts to suffer. Okay, so let's see, Mike. Okay, the transmit signal, we covered that. Measure the balun, we covered that. Okay, so we've got the expensive things. OSL values need to be entered somewhere. Yeah, so with most VNAs, professional VNAs, when you do a calibration, you actually need to put in some parameters for the calibration kit for the open, short, and load. In the case of the NanoVNA, it's just assuming an ideal open, an ideal short, and an ideal load. So that's the NanoVNA just assumes that, and when you select open, short, and load in the cal process, it's just assuming those ideal values. So you can, in theory, you could use standards that are really any impedance as long as you know what they are. And then, so if you know this, the impedance of this is 43 plus J20, if there was a way to put that in there and you put that standard on there, whatever error there was from that actual measurement would be used as part of the calibration. In the case of the NanoVNA, it's just assuming an ideal 0, an ideal infinity, and an ideal 50. Okay, so there's no place you've got to enter it in because it only works with those. Some of the external software might allow you to use a non ideal cal standard, but I'm not familiar enough to tell you that. Okay, does a calibrated spectrum, this is from Mike, W2AEW, does a calibrated spectrum analyzer with a tracking generator yield most of the desired results that you get with a VNA except for the easy phase angle measurement? And the answer to that is yes. If you're only looking at magnitude results, okay, and you don't really care about phase, a scalar network analyzer, which is effectively what a spectrum analyzer and a tracking generator is, will give you equivalent results. So, so certainly that's true. Gary, KI7VUX, would you use this to tune the inductor in an LC trap? You certainly could if you've got a way of actually measuring the trap itself. Again, measuring some of these physical structures can sometimes be a little tricky. But if the trap is in an antenna and it affects the match going into the antenna, you certainly could be looking at like the return loss plot or reflection coefficient plot and adjusting the trap to achieve what you want to get. So I would say yes. If you're measuring the trap by itself, it might be a little bit trickier. Is there a way to measure the velocity factor of a cable? The answer is yes. If you can measure the physical length of the cable, then you certainly can, right? If you know this cable is 50 feet long or 20 meters long or whatever it is, you know that's how long it is, and then you do a distance measurement, using the transform, the ratio of those two is the velocity factor. Okay, so so you can certainly use it. If you don't know the length of it and you don't know the velocity factor, then you're kind of out of luck. You need to know one to get the other. That was from Shirley, KE1L. Now, John, KC0G, is it worth using a short SMA to BNC adapter to save the SMA connectors with the NanoVNA? It certainly could be. If most of your interconnects are going to be BNCs, then you could actually put a little adapter on there, and actually can even make yourself a BNC calibration kit, open, short, and load, and then do all your calibrations to the end of the BNC connector, and then just leave them connected permanently. I don't know if you guys have got my video up or not, but I've actually got some SMA, what are called connector savers attached to mine. So I do all my connections to these connector adapters. I did my calibrations to these connector adapters or connector savers, so that if I damage this or I wear it out by using it a lot, I can pull it off and put another one on. So I save the wear and tear on the SMAs. But certainly if you have another connector style that you use most often, like a BNC, you can certainly use that and run the calibration to the end of that, or even use port extension to the end of those adapters. So Ian McCrum, what's the difference between the SAA2 and the earlier NanoVNAs? There are some hardware differences. I haven't looked into the schematics of the SAA2 to tell you, but they supposedly made some improvements in the measurement dynamic range because of the way things are built. The biggest difference is the fact that it goes up to 3 gigahertz, where the other NanoVNAs go up to like 1.5 gig max. It does have, again, better performance. The other big difference in terms of the way the firmware works is that it does not do interpolation between your calibration points. So what that means is you really have to run a calibration anytime you change the measurement frequency on the SAA2. Let's see. Scott, KA9P, can you suggest any reference for an intro to a non-50 ohm system analysis? The problem I'm thinking is most analysis of vacuum tube IT transformers, unknown high impedance. Unfortunately, I don't have a good reference there. Most of my work is in 50 ohms, so I don't do a lot other than that. Certainly, a couple of sets of known transformers could be used. Okay, if you've got a 4 to 1, 9 to 1, whatever, a couple of transformers you can use. And then you have to do your own calculation in terms of what the other impedance looks like. But certainly, like crystal filters are often not 50 ohm input and output. They're typically a couple of 100 ohms. You're going to want to put some impedance matching transformers on either side of that to accurately measure those filters, for example. But same type of a problem. Unfortunately, it's not something I've done a lot with now. I believe that Wes Hayward actually just published a a nice paper on some crystal filters, and he might have some measurement techniques in there. He also wrote a paper about a year ago on the NanoVNA itself and talks a bit about measuring non-50 ohm devices. So I'd suggest looking at Wes's site there. From Dave, G7WHI, to keep in mind, one thing to keep in mind with using the NanoVNA as a gas spectrum analyzer is that you will see the reference signal as well as the signal you might be interested in seeing. That's true too. So if you don't have the reference signal connected, you might still get some feed through from that as well. So that will certainly limit the dynamic range that which you can measure with. And Chris asks, am I going to get the NanoVNA V2, the SAA V2? I'm going to wait until it's more widely available with a 4-inch display. Some of the firmware issues have been bugged out, and maybe some enhancements to do the interpolation between points. So I'm going to give it a couple of months before I make that decision. I'm happy enough with the H4 that I have now. But there's always active work going on with these type of projects. So I think I'm probably a few months away from making that decision. So let's see, AA7G and SM5LW, Gert. What about the need for phase stable cables between the VNA and the DUT? That's a great question, Gert. So the cables that you connect up to the device, the phase actually can change on many cables just by physically moving them. And depending on the length of the cable and the frequency you're measuring on, it might move substantially. And if you really need to make accurate phase measurements to a DUT and you carefully calculate or calibrate right at the DUT, and if you physically move the cable, you might change your results. And you can actually run that experiment yourself. If you really need to make some very consistent measurements and you don't have these very expensive phase stable cables, just tape everything down to your desk, right? And don't move things. Do your calibrations, connect your DUT without moving the cable much. If you just have to move the end to make a connection, that's not going to really change the phase, probably not going to change it enough to cause a problem. So if you keep everything kind of stable, but if you make a connection over here, and then you connect the thing up over here, you might get a change in that phase. And again, if phase is important for the measurements that you're making, then you want to try to keep the cables in the same physical orientation from when you did the calibration. And then the last question I have here, I believe, is from George, DL1CLX. Do you need to solder the coax to an RF filter? How much will that affect the calibration with SMA connectors? It's a good question. If your filter does not have the connector on it, it's not connectorized, and you need to measure that. Soldering the coax to it is one way. Soldering a connector to it temporarily to make the measurements is another way. If you've got 50 ohm lines going into the filter and out of the filter, you might be able to connectorize it or make the calibration at a different point and apply the port extensions to get up to the filter location. That would involve, maybe doing a little solder bridge right at the filter connection after you've done the cal, then use the port extension to kind of get rid of that delay as seen in the Smith chart, and then remove that solder bridge and make your measurements. So how much it affects the measurement is really going to depend on how much of a delay you've got and what frequency range you're measuring over, right? If you're measuring filters in the HF frequency range, it's not going to matter that much. If you're measuring a filter at 1.2 gig or something, it might matter more, right? The higher you go in frequency, the more things are going to matter there. So, and then we've got Mike, G4GUG. Is it possible I could review the pros and cons of available ham cost VNAs, make a judgment value? Well, I think that probably nothing compares to the NanoVNA in terms of cost. Even like I've got a Rig Expert unit that's kind of like a single port VNA. It does Smith charts and complex impedance, and that costs $350 US. Is it that much? Is it that's what 6 times what the NanoVNA cost? Is it 6 times better? How you're going to? The answer is it depends. Right? I've tried using the NanoVNA outside. The display gets completely washed out by the sun. I really can't see it. And it's also pretty lightweight, and I don't know that I'd trust dropping it on the ground Whereas that Rig Expert, I would, if I dropped that while I was making a measurement outside, I wouldn't worry about it. I can see it outside, it's readable, and so it's easier to use from that standpoint. So it really comes down to what you want to use it for, what your use case is. But some of the other VNAs that are available, like from Array Solutions and things like that, there's a couple of other ones that are out there. I unfortunately don't have any experience with them to tell whether they're better or not. Most of them will likely do more than 101 points. They probably have got better dynamic range, certainly at the higher frequencies, because I don't know that they all use a simple square wave as the output, but it really comes down to what level of performance you need. So unfortunately, I can't give you a complete answer, Michael, because I don't have some of the experience with some of the other instruments that are out there. So the same thing with Mike also asking about the SDR kits in the UK. Unfortunately, I don't have firsthand experience with it. So that's one of those things that even on the NanoVNA forum or some of the other forums, you might be able to find some folks that have got a better comparison. I just don't have a real good comparison for you. So I think that's the questions that I had here. I don't know if anything popped up in the chat. I don't have the chat open. If there was anything else, but did I miss anybody's there that you can see?
No, I think we've come to the end of the questions, and there were some interesting comments in the chat. Can't get right to them right now, but thank you very much. That was a
Sure.
very informative presentation.
Oh, thank you.
I appreciated it a lot. So unless anybody else has any more questions or comments, I think we'll bring this thing to an end. We're a little over time here, but it turned out well, I think.
Yeah, the advantage of being the last one of the day.
Right.
Yeah, not quite the last session. So Alan Wolke, brilliant presentation as ever. And for those that haven't seen your YouTube channel, loads of stuff on there. So thank you very much for coming today. And Glenn, thank you for hosting that event. What I'm going to suggest is, because we're going to start again in 10 minutes with a presenters panel. So we're going to take a 10-minute break. So I think all of us that are panelists and hosts and co-hosts, if we all turn our audio and video off literally for 10 minutes rather than close this down and restart it, which I think is a bit of faff for everybody. As participants, none of you will get logged out, and we're going to bring as many of the presenters together again at in 10 minutes time to answer any more questions and say a few words, and then we're going to do a few other bits before we close the whole event. So if you don't mind, I'm going to keep quiet now, and we're going to suggest that we all do for 10 minutes, and we'll restart again in 7 minutes time at 1640 UTC.
That's great.
Cheers,
that'll
Alan.
give me time to go through and read all the chat.
Yeah, cheers, Alan.
All right, thank you. Bye-bye.